Alright, before we start, I'll recommend you to watch these videos first. If you're done, let's get into it. In previous videos, we know about massive particle which has characteristic or parameter as m mass, which this is found in Newton's law, Euler's law, and etc. Newton's law explains general motion with mass as dynamic parameter or inertia parameter, and then on Euler we have rigid body that generalized to inertial tensor and etc. And now we have defined new thing we call field, which different in mathematical algebraic definition, which in example we have electricity and magnetism phenomenon in our daily life. Now, what is these two? In this video, we only discuss about electricity first. Before 70 and 85, the scientists found that some objects attract to amber, which now we know as static electricity. And then in this year, by Coulomb invention that describe electric effect to some object that electric force proportional to 1/r squared or inverse squared law, similar to gravitation. This law, or known Coulomb's law, states that force because of electricity interaction equals to Q1 multiplied by E factor 2 is equals to Q1 multiplied by Q2, then inverse squared law, and the constants, which the epsilon relate to electric permittivity and it relate to medium response due to electricity. And here in yellow, this value is about electric field because of number 2 source, which inverse squared here related to field that different between local point. And fun fact, epsilon 0 here, 0 relate to vacuum as medium, and direction of E factor here is about in E direction. By the equality before, here we know that electric field is a vector field with direction E hat, and it's generated because of Q a scalar value, which here Q is charge, and we compare to the m or mass as inertia or gravity parameter. By analogy, charge in electricity phenomenon, but m here in mechanics, which all particles can have one or both from these two to characterization or parameterization. Now, imagine that we have two particles with similar mass but different in Q or electric charge, which one here is Q prime, and by third law of motion, we have this force is equals to P4, and then the next equality by third law. Now, we have the same set of charge and mass, but in different configuration position, we will have the same F formula here. So then, if we place the particle in origin point with mass m and q electric charge, then we have electric field generated as this, which here we can imagine there is a pillbox like this and we can squeeze into infinitesimal size. So by divergence theorem, this charged particle being the source for magnetic field as this equality when epsilon here come from this as medium, and of course the next equality too. Here, we restate that epsilon is medium parameter, which for special case epsilon 0 here is a constant. So here, if we define the total electric charge Q is equals to this integral, rho here is charge density or Coulomb over volume. So then Q over epsilon 0 I can replace with this integral, and if we compare with next equality by divergence theorem, we will get that the result will be this, or known as Gauss law for electrostatic. And here we notice that the rho relate to distribution of charge or the charge density. So here this rho is a field, or we can define a function of position and time. So by general, this is universal, but here we will focus on electrostatic or without time. Here we have more questions. What about the curl of electric field? In electrostatic, which means the charge is in rest without moving, so we have electric field around the charged particle as this. Then here we take arbitrary loop here 1 and 2, and then we see that the dot product for all possible loop here is equals to 0. So for electrostatic case, this nabla cross A will equals to 0 vector. With this result, if we use Helmholtz theorem for irrotational vector here, then we can define electric field equals to some gradient of scalar function, let's say minus V here, or in the future, we know this as scalar potential field or electric field potential. We choose this kind of function because about the electric field here, I will explain in future videos, which in curl, we have this is correct, but here in dot, this is not necessary equals to 0. So by substitution, in the first equations, the result will become as this. And this result is about Poisson partial differential equation. Partial differential because of this squared nabla as a scalar operator, and for rho is equals to 0, then this equation will become Laplace partial differential equations. And fun fact, this scalar operator squared known as Laplacian or similar to second derivative in one dimension. That's a simple approach for electrostatic using vector calculus and the others. I hope you enjoy this video. If you like this video, don't forget to share and subscribe. If you have any questions, just post the comment below. And that's it. See you later.